Okay, so I'm going to start off and review some of the things that we just covered in class, and then we'll do a couple more examples similar to ones that we've done in class. So what we talked about in class, in the last class, is this idea of a sampling error. So what we do in inferential statistics is we collect some information about a sample and use that information about the sample to draw conclusions about the population. Our sample can never be a perfect representation of the population. There will always be some error, some uncertainty in how well we know the population given the size of our sample. And we call that the sampling error. So if we are interested in some mean values of the population, so we want to know on average how long does it take a student to finish this test, we sample one class and we see how long it takes them on average, and we use that to draw some conclusions about the population. But when we get into the nitty-gritty of statistics, we can actually see how long it takes a student to take a test in our sample, and we can know with a fair amount of certainty how wrong that estimate of the sample can be drawing conclusions to the population. So, and that is at the heart of chapter 7 and the central limit theorem. So a couple of things. Properties of the distribution of sample means is that if I take a sample from a population, and the size of that sample is n, there's n different observations. There's 30 students in the applied statistics class. The mean of the variable equals the mean of the population. Okay, so the mean of the sample mean is the mean of the population. For samples of size n, so for the 30 students in the class, the standard deviation of the mean equals the standard deviation of the variable under of the variable that we're looking at divided by the square root of the sample size. So the standard error of the mean, how far off this estimate of the mean based on the sample could be, is the standard deviation of the population divided by the square root of the number of samples. And these are the two properties that govern what we've been talking about, and I think they're easier to understand in practice. So let's do some practice. We started off talking about one example that we did in class was the average of one die. So if we threw 10,000 tosses of a die and we got a number between 1 and 6 every time we tossed it, with more or less equal chance of rolling a 1, 2, 3, 4, 5, and 6. No more or less about it, excuse me. You have an equal chance of rolling a 1, 2, 3, 4, 5, or 6. And so in this simulation of 10,000 tosses, we see this pretty much horizontal distribution. It's not perfect because we haven't tossed it an infinite number of times. We've only tossed it 10,000 times. We have a horizontal distribution. And the question that we considered in class is that, well, what is the average roll that you get when you roll a die? It's somewhere between 1 and 7, and it's actually 3.5. So on average, if you roll a die a whole bunch of different times and you average together all of them, so one time you roll a 1, and then a 3, and then a 6, and then a 5, and then a 4, and then a 3, and then a 3, and you keep going, eventually you average all those numbers together, you'll get a number somewhere between 3 and 4. It should be about 3.5. So 3.5 is the population mean. Right, that's the average that we get, average value when we roll a die. Okay. So if I took 2 die and rolled it and took a random sample of 2 from this population of 10,000 and looked at the average roll of those die, every once in a while I'll roll a 1 and then a 1, and that would be an average of 1. Every once in a while, I'll roll a 6 and a 6, and that would be an average of 6. Most of the time, I won't roll 2 1s or 2 6s, so most of the time, I will get somewhere in the middle. And it turns out that the most likely roll that I can get is going to be a 3.5. And so I think I just want to talk about this figure first, and then I'll explain the text. Right, if I took a sample of 2 dice, sometimes I roll a 1 on average. That's rolling 2 ones. Sometimes I roll a 6 on average. That's rolling 2 sixes. Most likely, I'm rolling a number somewhere in between, and 3.5 is the most likely roll that I get. So the mean of my sample, and I took now a whole bunch of samples of the roll of 2 dice, the mean value here is 3.5. The mean of the sample equals the mean of the population. The mean of the sample mean equals the mean of the population. That is this equation here that we wrote down there. Okay, so I take a sample of 2 die, and I have a mean of 3.5. But there's some non-zero probability that I roll anything between a 1 and a 6 on average. If now I roll 20 dice, the chance of me rolling 20 straight ones, it's not impossible, but it's really, really, really unlikely that I would roll 20 straight ones. And so what we tend to see here is that we start to get this clustering of the mean around 3.5. So 3.5 is the most likely average that we get when we roll a bunch of die. And 20 dice is now enough that we get this distribution that's really tightly clustered around the mean. So as our sample size gets larger, as we go from 2 up to 20, our estimate of the population mean, our estimate of the true mean that we are looking for from the population, which is 3.5, gets better. Right? We get closer and closer to knowing that this is 3.5. Okay, and I guess the mathy way of writing that, so I can show you from this how this falls out from this second equation here, which says the standard error of the sample mean is the standard deviation of the population divided by the square root of n. How that is manifest here is that the standard error of the sample mean, that's kind of like something like the width, the mean plus or minus 1 standard deviation of the sample mean. So the standard error, the standard deviation of the sample mean depends on 1 over the square root of n. So as n gets bigger, as we go with more and more and more samples, our error in the estimate of the mean gets smaller. Because if the number here in the denominator is getting bigger and bigger, the number here in the numerator has to get smaller and smaller. So this equation here is saying that as our number of samples gets bigger, the width of this distribution of the sample means gets narrower and narrower and narrower. In other words, we know more and more precisely what the true population mean is. So as we have more and more population, more and more samples, our estimate of the sample mean gets much better. Okay. Okay, so let's do something new. Here's an example. The winner of the 2013 NBA championships was the Miami Heat. How many teams ago was this for LeBron James? It was at least 1, I'm pretty sure. Possible starting lineup for that team is listed below. So we have 5 players as a starting lineup for the 2012 Miami Heat. And we're looking for information about the height of these players. So they range from all the way as low as 74 inches all the way up to as high as 83 inches. So the population mean height of 5 players is this plus this plus this plus this plus this divided by 5. So you could do it as a list on your calculator. I'll just write it out. So it's 83 plus 76 plus 80 plus 74 plus 80 divided by 5. And that I got to be 78.6 inches. Okay. So there's nothing new in there. So we have a population of only 5. And we're taking a really small population here so that we don't have to deal with 10,000 things to write down. So we're using this as an example to kind of help us construct distributions and understand what they look like. So for part B, we're looking for a sample of size 2, and I want to make a table of samples and means for each sample. So I want to make a table that looks like, we'll say, the thing that is the sample, and I'd write and the sample mean as well. So this is like the example that we did in class where we were taking a sample of 2 from the population of 4 numbers. So now we're taking a sample of 2 from the population of 5 numbers. If you think you know how to do this, now would be a great time to pause and do it and fast forward to the end and see if you got it right. And if you didn't, go back and rewatch it. So for my samples, I'm going to say, now I'm not going to list samples that have replacement because I can't have Chris Bosch in here twice. So I'm only going to have, I can have Chris Bosch and Wade, Bosch and James, Bosch and Chalmers, and Bosch and Halsem. And that would be the different samples that I can have. So I'll go ahead and write B and W just so that I'm clear on what I'm writing here. And so that sample is 83 and 76. And the sample mean of that sample of 2 is 83 plus 76 divided by 2 is 79.5. So my sample mean of my sample of 2 is 79.5. That's one of the sample means that I could get for this sample. So there are a lot more than just the one. So now would be a great time to pause if you haven't already and fill out the rest of this table. And when you have done that, to unpause, and I have the total table written right here. So I have B and W have these 2 heights and the sample mean of the average between them. I could also have B and J with these 2 heights, and there's the sample mean. I could have B and C sample those 2 heights and this sample mean. So I can go through and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible 10 possible samples of size 2 that I can draw from this population of 5. Okay, so we've constructed our table of the samples and the means of each sample. Let's draw a dot plot for the sampling distribution of the sample mean of sizes 2. So we're going to make a dot plot instead of a histogram because we have only 10 numbers here, so it's not that hard. When you're writing a dot plot, I can't stress enough how important it is to actually draw these things on a to-scale axis. So, and what I mean by that is I don't want you to plot, what's the lowest number here, 75. I don't want you to go, here's 75. Okay, so there's a dot at 75. What's the next lowest number? 77. So there's a dot at 77. There's my dot. What's the next lowest number? 78. There's a dot at 78. So this isn't, I keep putting dots down there. This is not to scale, right? So there's one space between 77 and 78, but there's 2 spaces between 75 and 77. On the midterm that you guys had, a lot of people didn't draw their dot plots to scale, and you missed points by that. And so this is what I mean by that. So when you draw your dot plot, draw the axis first. So this goes down from a low of 75 up to a high of 81.5. So 75, 76, 7, 8, 9, 80, 81, 82. Okay, and now I'm ready to fill in my dot plots. So I already have a axis that is to scale, and now I can put the dots on it. So I want one at 79.5. So there's one at 79.5. One at 81.5. One at 78.5. One at 81.5. Second one there. One at 78. One at 75. One at 78. one at 77, one at 80, and one at 77. Okay, so there's my dot plot of the sample means drawn from a sample of 2 from the population of 5. Okay. So let's keep going with this. I want a couple more questions. And I'm actually going to cross this off and make this D and E. So for the same team, for this random sample of size 2, what is the chance that the sample mean will equal the population mean? So what's the probability that you randomly picked a sample of size 2 and the sample mean actually gave you the population mean? So what's the chance that you're right just by picking 2? So let's go back to our table where we said that the sample mean is 78. Oh, I think I didn't say this right. I want to say that the sample mean is within 1 inch of the population mean. Right. We don't need to be exactly right, but let's just say that what's our sample mean to be within 1 inch of the population mean. So we want, here's our population mean. What are the chances that we drew a random sample of 2 here, and we happen to pick 2 where the average value was close to the true value, where the sample mean was close to the population mean. So we're looking for things between 77.6 to 79.6. So there's one. I guess I should put a star. There's another one. There's another one. 78 is good. 77 is not good. 80 and 77 is not good. So if I randomly picked one of these samples, 4 of them fall within this range that's within 1 inch of the true population mean. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the chance that I randomly picked something with a sample of 2 within 1 inch of the population mean is 4 possibilities, 4 of the stars divided by 10, which is 0.4 or 40%. Unless the problem specifically asks you for a percent, you always write these things as decimal numbers. Let's say that again. Unless the problem asks you for a percent, probabilities are written in decimals, not in percents. Okay. So for a random sample of size 2, what's the probability? Oh, now I see that I didn't read my problem all the way. So I just did number E. So for a random sample of size 2, obtain the probability that the sampling error made in estimating the population mean by the sample mean is 1 inch or less. That is the number that we just answered. So we are within 1 inch 4 times. So our answer to E is 40%. The answer to D is for a random sample of size 2, and now I will keep it how it was. What's the chance that the sample mean will equal the population mean? And the answer to that, which is why I originally skipped over it because I forgot what my own question looked like, is 0. Right? None of these are 78.6. So we have a 0% chance that we pick a sample of size 2 and we get exactly the right population mean. Okay. So I want to make sure that I'm careful here about using my words. So let's interpret these results in terms of percentages. So we found that the probability was 0.4. So that says that if we took a random sample of 2 heights, there is a 40% chance that the mean of the sample will be within 1 inch of the population mean? Okay, so in words, that's what that means. The probability is 0.4, so that our random sample of 2 has a 40% chance of being within 1 inch of the population mean. Okay. Okay, so next is a topic that I'm sure none of you know anything about. So alcohol consumption on college and university campuses gains attention because undergraduates tends to drink quite a bit more than people of the same age who aren't students. So researchers call this binge drinking. Researchers found that students who were binge drinkers drink many times a month with a span of each outing having a mean of 4.9 hours and a standard deviation of 1.1 hours. So that is saying that our population, the population of all university students who are binge drinkers, when they go out to drink, they go out to drink for on average 4.9 hours. But the standard deviation of this, so 2/3 or so of the binge drinkers are within 1.1 hours of 4.9. So for samples of size 40, find the mean and standard deviation of all possible sample mean spans of binge drinking episodes. Interpret the results in words. Okay, so I have a sample of size 40. So if you already think you know how to do it, now would be a great time to pause and make sure that you know what you're going to do. Think about what equation are we going to use. So we want to find, we're going to take 40 out of this whole population of all undergraduate binge drinkers and find the mean and standard deviation from that. So that is that the standard deviation is 1.1 hours. I'll throw this formula over here again. Remember this formula? The standard error of the sample is the standard deviation of the population, which we know. That's 1.1 hours divided by the square root of the number of samples. That's 40. So that is the standard error of the sample is 1.1 divided by the square root of 40. And that is 0.17. Okay, so we'll do let's write those answers down, and then we'll do the part about interpreting in words once we're done. Never mind. So let's continue with this. Okay, so what does this even mean? What does 0.17 hours mean? So we know that they go out for 4.9 plus or minus 1.1 or so, right? That's the standard deviation. So what does this 0.17 even mean? So if we took 40 of them, chances are we would get about this close to the true standard, the true sample mean. Okay, so for samples of size 40, the mean and the standard deviation spans all possible. I'm going to write this down and then we'll explain it. Okay, so a sample, if we randomly grabbed 40 of those undergrads, then that sample that we grabbed would probably be somewhere near 4.9, but there's sort of a, I don't know, a 2/3 chance that it would be as low as 4.9 minus 0.17 or as high as 4.9 plus 0.17, because I know that about 2/3 of all observations fall within one standard deviation of the mean, and this here is one standard deviation away from the mean. I think maybe a more illustrative way to write this is part B. And you have a question like this in your homework. So how much variation would you expect from your answer in part A? And the hint is to use the 3 standard deviation rule. The 3 standard deviation rule, if this is, that's the empirical rule that we wrote before. I think we're getting pretty good at identifying that within one standard deviation of the mean is 68% of the data, or 2/3. That's why I usually say 2/3. 2/3 is actually 67%, but it's a nice thing to round. Within 2 standard deviations of the mean, that's 95% of the data. And within 3 standard deviations of the mean, now you're all the way out here, that encompasses 99.7% of the data. And I think the word that your book uses is this is virtually all of the data. So virtually all of the data are within 3 standard deviations of the mean, because for normally distributed data, 99.7% of all observations fall within 3 standard deviations of the mean. Okay, so in this question, how much variation do you expect from your answer in part A? The question is asking, okay, so the mean of all possible samples of size 40 that we could have drawn is 4.9 hours. But if we just randomly pick one of those samples of size 40, how much variation do we expect in that? How far away from 4.9 could we be? How wrong could our population mean, or our sample mean be in estimating this population mean of 4.9 hours? So let's use the 3 standard deviations. So 3 sigma rule, 99.7% of the time, we expect the sample mean to fall within 3 standard deviations of 4.9 hours. So 4.9 minus 3 standard deviations times this 0.17, which was our standard error of the mean, that equals 4.39. Check it to make sure. 4.9 minus 3 times 0.17, 4.39, and 4.9 plus 3 times 0.17 is 5.41. Okay, so if we randomly picked a sample of 40 undergraduate binge drinkers and we took the average number of hours that they stay out when they stay drinking, virtually all, 99.7% of those samples, so virtually all of those samples would fall between 4.39 hours and 5.41 hours. Okay, so this is another way of saying this is that given if we randomly sampled these 40 undergrads, there's virtually no way that we would sample all 40 of them and get that on average they stay out for 2 hours, or get that on average they stay out for 10 hours, because 99.7% of all of the samples of size 40 that we can pick will get a number between 4.39 and 5.41. So I think this is a really useful way of looking at the problem. As our population gets bigger, this standard deviation should get smaller. Another way of saying that is that the more, let me back that up. I said population when I meant to say sample. As our sample gets bigger, so if we were to sample more than 40, that would mean that our standard error of the mean, the standard deviation of the mean, would get smaller because we'd be dividing by a larger number here. And that means that our error in our estimates of the population mean, the true mean, which is based on this calculation that we'd be doing on a sample, will get smaller and smaller. So I think that is the next question. So repeat part A, but for n equals 120. So if we instead of only taking 40 students, we took 120, I'd find that the standard error of the sample mean is 1.1 hours divided by the square root of 120. I got 0.10. So if I asked again the same question up here, which I haven't asked, in taking more students, we would be doing a better job of hopefully representing the population from our sample. And that is represented in the fact that our standard error of the mean is only 0.1 hours down here, whereas it was 0.17 hours up here. Okay. So what's on Thursday's quiz? Thursday's quiz has just one problem on it. It's a question from section 6.3, and it will be similar to these three examples that we did in class last Thursday. So we did these three problems. I think they are posted on the notes from last week, and the problem will be very much like this. So go through. So here's a college entrance exam is designed so the scores are normally distributed with a mean of 500 standard deviation. Of 100, find the percent of subjects with scores between 550 and 675. So you're taking this and turning the numbers into z-scores and then finding the probability between two numbers. And actually, I'll get rid of this one because that one won't be on the test. So it is a just fine question, but this sort of eliminating the lowest and highest percents of the thing is not specifically the format of the questions on the quiz. Here's another one that says test scores are normally distributed with a mean of 72 and a standard deviation of 13, and we want to assign a grade to the top 15% of the students. So we are looking for a z-score of the area to the left of the curve to be 85%, so that we can assign the top 15% of the students that A. So we looked for a z-score of 0.85 and then backed out what that z-score should represent, and it was an 85.52. All right, so between these two examples, in one we are taking normal numbers, changing them into z-scores, and finding the area under the curve between them, or to the left of them, or to the right of them. And the other, we are looking at percents, so we're looking at percentiles, and having to calculate that from there. So it'll be a multi-part question with several steps along the way, several different things that I want you to do.